So this meeting is recorded, and after the session, we will share the presentation, the slides, and the recording itself. We'll also share some useful links for you guys. And as I said, if you have any questions, please ask in the chat, and we'll be able to address that. So yeah, as we said, we'll talk about supercharging your quant models and how you can use Python in production. And we've already seen that people have concerns about risk calculations, performance, about the stability. And with Matlogica, we can help you to address that. And today I'll be presenting some of the theoretical background, and Dmitry Golubentsev, our founder, will talk about the practical examples and talk you through the code. So the plan today is, at first, we will go through a couple of slides just to get everyone on the same page. We'll tell you about what we do and who we are, and we'll have a few slides on how the technology works. And after that, we'll move to the exciting part that will be presented by Dmitry, where we'll talk about some code examples, such as mixing C++ and Python for your quant libraries, actually using Python alone, doing model calibrations, XVA, how you can serialize your workloads for cloud, how you can do life risk, and then we'll discuss what's next, and hopefully we'll have the time for the Q&A. We'll aim to finish in 1 hour, but in case we run over, everyone is welcome to stay for a couple of extra minutes to address any questions. So what we do, Matlogica AADC, and AADC stands for Adjoint Automatic Differentiation Compiler, and it acts as a layer of abstraction. So if you have your quant libraries and you have your hardware, with Matlogica, you can achieve superior performance. So you can achieve speedups of 1000x in case of Python and a bit less in case of C++. You can also mix C++ and Python, and you get very fast simulations and very fast automatic risks. So you have the same methodology, whether it's first order Greeks, second order Greeks, cross gamma, PNL explain, any of that, you've got the same method to compute sensitivities, and you also get excellent performance. And with that, your model development is simplified because you no longer need to think about the methods to compute risks or about optimizations. So you can turbocharge both the new and the seasoned quant libraries. And for new quant libraries, you can develop them from a different perspective. So because you don't need to think about aspects like optimizations and computation of risk or what hardware do you use to get optimal performance, you can make your architecture much simpler and achieve the performance not attainable by other means. And we also have, for those of you who have a quant library already, be it based on QuantLib or something else, we have a simple and semi-automated integration approach. So our clients see initial results in weeks. And in case of Python, we recently saw results achieved in 3 days with 15,000 performance improvement. So moving on, so what you would currently see in a typical quant library is that, well, you have your Monte Carlo simulation or maybe backtesting or stress testing, and you have a loop of executing a function which calls another function and another function. And in case of Python, it's an interpreted language. So the performance penalty of all the abstractions, virtual functions, and so on is on every cycle. And you have 10,000 Monte Carlo loops, it will be slow. And if you need to compute risks, whether using bump and revalue, well, that means multiplying your execution by the number of risks that you have to compute, or using frameworks like JAX or PyTorch, it will be slow because these are not designed for mathematical finance and handling large computational graphs. And your code is likely to be scalar and single-threaded. With Matlogica, you can address that. And the way it works is that for the first sample of your data, we will trace your operations using operator overloading, and we'll extract the evaluation graph, which is your primitive operation, plus, minus, divide, exponent, and so on. We'll take this valuation graph, and on the fly, we will transform it into a kernel for both the forward, which replicates your original function, and for the adjoint, which does the calculation of derivatives if you need it. And these kernels will use native CPU vectorization, so AVX2 or AVX512, and they are fully multi-thread safe, which means that your simulations will be 1,000 times faster, and your adjoint risk can be computed faster than the original function itself. So as a step 2, when you are doing your Monte Carlo loop or your what if or backtesting, instead of calling your original function, you call the kernel that is the exact replica and produces exactly the same numerical results, but is so much faster. I mean, you cannot achieve this kind of performance in any other way because it uses all the capabilities of modern CPUs to like 100%. Like if you were writing machine code, you could get this, but who writes quant models in machine code or assembly? So yes, as a result, we've got automatic vectorization, AVX2 or 512, so that's 4 or 8 samples of data. You have multi-threading, even if your original program is not multi-thread safe. And you have out-of-the-box automatic adjoint differentiation. Therefore, your simulations and risks are much, much faster. And that enables you to get live risk, to save 50% and more in cloud or compute. And as a business, you can make better decisions in terms of hedging, trading, or even prioritizing the features that you want to get to the market. You can also do the mixed mode execution of Python and C++, and we will see an example of that. You get 10 times faster than JAX and PyTorch. And the kernels are also serializable and secure, so you can send them to the cloud, and you don't need to expose any of your models or your proprietary data like trades, portfolios to the cloud, because we just generate the binary code, you can ship it to the cloud, and you can enjoy faster execution. Now, getting to the fun bit, we've got 5 use cases with code examples. In the first one, we'll start with the first principles. We will look at the Monte Carlo example just to get the basics of this. Then we will look how you can use Python only for the example of Sabre volatility calibration. After that, we will see how it scales. So we will use XVA live risk and see how the performance improves from AVX2 to AVX512, and also how it scales with the number of threads that you add. Then we will look into custom curve interpolator, where we will serialize the workflow for cloud, and we will see how to use C++ and Python together. And finally, we will look at the live risk based on the automated implicit function theorem. And with that, I will hand over to Dmitry, and I'll talk to you a bit later.
Thank you, Natalia. Thank you for this introduction. It's my pleasure to see you all at this webinar. I'm going to share my screen in a second. It would be nice if we can confirm it's working. Yes, I can see it's working fine. So today we're going to look at a bunch of examples. Matlogica was originally focusing mostly on hardcore C++ quantitative libraries. We recently made a great expansion into Python space, and we see amazing results in this area. More than just supporting Python, like many other frameworks do, we do put a lot of effort into making sure C++ and Python can work seamlessly together. And as a quant with a lot of years of experience, I found that some of the features fascinating. So all of these examples available on GitHub. You can head to github.com /matlogica ADC Python. We will be providing the link later in the follow-up email. You can run these examples in Google Colab. However, Google Colab is fairly limited in terms of hardware it provides for you. So, of course, to get the best performance results, you probably want to use your local machine for execution. So we're going to start with a basic hello world. Yeah, I know it's maybe not as exciting as serialization, cloud, and XVA, but we're all here to learn about low-level Python and how it can help you to build models in quantitative finance. So we need to first learn some basic concepts on how ADC paradigm works. So the basic hello world example, Natalia did fill you in that the approach we take is by executing a single sample of your original algorithm, be it implemented in C++ or Python. And I go through the steps that require to do that. So here I'm installing ADC Python module, loading it into the Jupyter, and this is the function we want to experiment. Now you can see the function itself, it works with regular NumPy operations. It takes types that can be arbitrary, it can be scalar, it can be NumPy arrays, it should function. And the function can be implemented somewhere else, right? So for this hello world example, we place it here, and we want to just see how what we do can work in this instance. So we next create an object to hold our kernels. So the kernels is essentially optimized machine code. This machine code can execute your calculations forward, meaning from inputs to outputs, but it also can calculate a backward propagation or adjoint risk. So it can propagate your adjoints from outputs to inputs. And let's see how it works. Instead of using scalar numbers, so in Python you can write x, y, z equal to 1, 2, 3, we're going to wrap these variables into I-double objects. So these objects allows us to trace calculations. So when your original program runs and execute primitive calculations, we're getting callbacks about the elementary operations your program executes. So this approach quite common, and it's called operator overloading in C++, where you substitute your native types with more complex types that behave almost like native types, but do some extra work. So here we have our XYZ setup, and we're going to call start recording to initiate recording of our evaluations. We also can identify what variables are actually inputs into our evaluation graph. There's not always variables that participate in calculations are actually something that is changing in your Monte Carlo simulation, right? In a basic setting, your Monte Carlo simulation can only take random numbers as inputs, and the rest can be hard-coded in efficient kernel. This is what makes it fast and efficient, because you can identify what variables are changing, and the rest will be automatically optimized out. So in this instance, we have just 3 inputs. We're running this expression, and we want to calculate the output of this function. So f, we identify it as output of this evaluation graph. So once you call the stop recording, your efficient kernels supporting AVX2 vectorization in this case is formed in memory on the fly, right? So you don't really launching any external compiler. And although ADC is called Automated Adjoint Differentiation Compiler, we're not working, as you can see, we're not working with the source code directly. We're working with the elementary operations that define your evaluation graph. So now this is a safety check, and we'll come back to it later to explain what it means. For now, it's just we pass this check good, so we can continue. So now we have a recording of one sample. So what can we do with this? We can run it for many samples. And this is a situation very common in finance, right? You want to record, you want to run same valuations over and over again for multiple inputs. It could be what-if analysis, it could be Monte Carlo simulations, it could be historical data, it could be historical VAR. But essentially, we recorded a one evaluation graph, and now we're preparing inputs, vectorized inputs, to run more samples. And this is what you see here. So for X, we're going to provide a random vector of length 20. And for Y and Z, we're going to use scalar data. Now, ADC wouldn't be automated adjoint compiler if it wouldn't also allow you to calculate sensitivities. So our interest not only to calculate output of the function, but we want to calculate derivatives of output with respect to all of its inputs. And this is what the request is. So here in this data structure, you can explicitly say what output you want to see and what derivatives you want ADC to compute. And now this is the high-level call allowing you to provide all this vectorized data as input, the request, and also you can say how many threads and how many CPU cores you want to run it on to produce back vectorized data. And here we have it. So this is the basic hello world, so nothing exciting here. We have the function outputs computed in 20 different samples. And we have sensitivity of function output with respect to its first two arguments. So I'm sure this is pretty clear at this point. If it's not, please free to put any messages or raise a hand and ask a question. So now I'm not going to dwell on the idouble class, idouble object in Python space, but I do suggest you to look at second example we have available on GitHub. It's called basic idouble iterations. It will tell you what you can and what you cannot do with idoubles, right? Essentially, when you're not in the recording mode, when you're outside of collecting graph data, you can do with idouble everything you would do with the regular number. And you can see it in this example. So we can have a vector of rates, we have a vector of mixed values, scalars and idoubles. You can have a vector of only doubles, etc. Right? So you can call NumPy operations on it. You can call it on idouble itself or vectorized, and you get expected result. Now, when it comes to recording, you have to be more careful about it. And here I'm going to skip through some of this. Just continue run all cells on below. And here, what you cannot do, right? So this is type of operations that are forbidden in order for the framework to work. You cannot convert idouble to float type and then use it somewhere else, because this loses the trace of elementary operations in the evaluation graph. So what you do instead, if you do come across this type of operations, you will be given an exception. So you will know something isn't supported, and you need to handle it somehow differently. Now, how to handle it differently, we'll come to this a bit later, but you should understand that there are some corner cases in calculations that cannot be recorded. Again, this is a bit technical, so yeah, we're going to get to more exciting stuff now. But if you have any questions with this space, let me know. Now, more exciting stuff. So Python wouldn't be Python without NumPy, right? We know Python language is interpreted language, and although it's very convenient, it's object-oriented. It's very capable to provide various expansions, and people can build new modules to it. What it is, it's interpreted language, and hence it's slow. It's slow for numerical computations. It's small for simulations, etc. So people tend to use NumPy as a way to run more efficient simulations and numerical code. So how does it work with ADC? Right. So in ADC space, what we want to do, we want to be able to record typical quant analytic code implemented with NumPy expressions, NumPy concepts. So for that, we support various patterns that simplify this recording and allow you to do the allow you to support some code with little or no modification to original logic. So this is the example for NumPy. You can see that some of the expressions. So we do provide a wrapper for NumPy array. We call it ADC array, and you can initialize it with NumPy array. Okay? So this is explicit. This is how you would use it if you're targeting ADC framework from the beginning. And in this instance, we demonstrate we can mark full vector of NumPy arrays. We can call a function on this vector, and we can mark output of this array. So we able to record NumPy operations in this fashion. So it's quite important to support more operations in NumPy because I know we tend to use some basic stuff, but some complicated expressions in NumPy that tend to be quite popular with Quant community and Python developers, and somewhat difficult to support for this operator overloading pattern. So here are some examples of operations that can work out of the box with ADC. So you can see some basic operations here. They work, and as you can see, when you print value of these expressions, these come to us as ADC arrays full of I-double objects. And for each object, you can also see its value, but also it tells you what type of role this variable carry in valuation graph. So when you're collecting your calculations from inputs to outputs, each variable, you may have a flag whether or not it has direct or indirect connection to inputs. But also you can see if the variable requires adjoint, if you actually need to propagate adjoints through this graph node. And this is all available to you in the Python debugger, and you can inspect that. Now,
so shall we move on to Saber example?
I guess we can. So I invite everyone to go through these examples because they are quite important for Python developers. Of course, it's a bit technical, but we've put a lot of effort in making sure these operations can work. I just want to wrap up on a very important operation, and it's explained here. So we're not only supporting these so-called basic operations in NumPy, although I don't consider them very basic, but we also support important operations that require, as in our terminology, stochastic arguments. So, and a good example in quantitative finance would be local volatility simulations, where you need to interpolate in your local volatility surface based on argument that comes from simulation. And this could be the equity index, and we need to find a bucket, interpolation bucket, in a vector of sorted values. And this outcome becomes stochastic, right? it depends on individual Monte Carlo path. This type of operations is quite difficult to support, and popular frameworks such as TensorFlow and PyTorch, they have difficulties with that. In ADC, as you can see, we support sorted operation from NumPy, and we can also interpolate values from a vector based on stochastic argument. So this argument that goes into this interpolation is stochastic. This is a very useful feature for quantitative modeling. Right, so moving to our maybe a bit more exciting example. So calibrations. What we want to do in this example is to demonstrate how you can record the ADC kernel, be it very efficient machine code to calculate your function values. What it can also do, it can calculate a Jacobian for this function. And if you have a Jacobian, you have a function, you're going to use standard Python frameworks such as SciPy to run model calibrations for you. So in this specific example, what we're doing, we want to calibrate Saber parameters with the given black volatilities and find this is the typical problem people need to solve in quantitative space, right? So we implement objective functions, and you can see a typical quant code in Python. So we use NumPy, we use where. This is quite challenging to support, but with our framework, we can record these operations as well. And we use a lot of NumPy here. We have some Boolean vectors, some logs, etc., operating on vectors. So this code not touched, right? So it's written before. It operates on scalar types, or it can function on NumPy arrays. And we're going to run it with a regular Python optimization routine. So we have SciPy optimize. We give it a go on this data set using the residual function as our objective function to do the optimization. And we're going to time it. So we're going to see how long it takes to calibrate these Saber parameters for, in this case, we're running it for 1,000 times, and we're getting it done in about 5 seconds. So this is just regular Python. So now let's see what we can do with ADC. So with ADC, so we have a we'll load ADC module, and we can record the previously defined objective function in Python and get ourselves a kernel. So this is a wrapper allowing you to send a function as argument and identify what parameters this function take and what values we need to calibrate on. So here we're running the least square minimizer from SciPy package. We use our function as a goal function, recorded ADC kernel as a goal function, and we also have a Jacobian computed to you by ADC. And this time, full calibration of this same data set takes about 150 milliseconds. So it's a healthy acceleration by about, what is it? About 30 times in this case. Now we can take it further if we want to, but this is just something you get out of the box. Right, so some more advanced examples. So we, according to our plan, we want to cover XVA modeling in Python. And modeling XVA in general is very hard because you need to run a lot of simulations and you need to price full portfolio basically in one go, because you need to take a positive and negative sides to calculate CVA and DVA. This makes it a very challenging problem for quantitative community, let alone trying to solve it in Python. Here we have some basic example. I was browsing and I found some references on other people's work. They use quantitative, they're using C++ QuantLib to do pricing for interest rate swaps. They also use C++ to simulate one-factor interest rate model. And later on, they use they use Python to glue the whole thing together. Now that's interesting. I thought it would be interesting to see what ADC can do in this space. So what I'm going to do now, I'm going to run this example, and I'm going to let it run, because what it does, and you can follow this example, again, it's in the same repository. And I'm going to skip it through here, and I find that it's going to use 5,000 simulations to calculate CVA and DVA numbers in this case. So I'm going to keep it running, and I'm going to go into ADC-enabled version of this Jupyter notebook. Now, in ADC-enabled Jupyter notebook, let me see if I, hold on a second, I probably need to just start this. So what we do here, we installing not just ADC core, but we installing ADC core that also include open source QuantLib library enabled with active I double type. So what does it allow us to do? It allows us to record calculations that happen not only on Python, this is what we saw, not only in Python and NumPy, we saw it as well, but it also allows us to record what happens in C++ external library. And this is what you can see here. We enable QuantLib, and we take we define QL variable pointing to ADC version of QuantLib. So this ADC version of QuantLib, we largely using the same source code as before. Our modifications are minimal, and mainly we're changing stuff related to inputs, also changing number of simulations. So we want to modify from 5,000 to 1 Monte Carlo path, the one we want to record. And subsequently, we use ADC kernels to run full-blown simulations. So I'm going to skip through the boring part. Again, you can go deeper into this because it's on GitHub. And I'm going to focus on the recording and the ADC. So here we're starting the recording. We identify the inputs. Our input is interest rate scalar in this case, but also we define all our sorry, this is the portfolio, and we have some volatilities defined as inputs, so you can tweak that if you want, and calculate sensitivities too. And somewhere here we should see our credit curves. And we run a recording. So the stop recording as output, we want to see economic CVA computed and DVA as output, as well as portfolio values along time steps, right? So we want to see the full exposure for our simulation. So we're now going to run this recording, and this time for 5,000 simulations. And to do that, we're preparing inputs. So what are our inputs? The model parameters, volatilities, hazard rates, interest rate, but also our random numbers. So our random numbers are inputs into our simulation. And here in this instance, we pre-generate all random numbers. So ADC is not in the business of simulating random numbers. This problem is well understood. You have wonderful solutions of Sobol generators or MKL library to do that. So we put this outside of scope of our acceleration. And if you consider life risk, I think it's reasonable because you can pre-generate random numbers and store it in memory. And this is what we do here. So we spent about 0.6 seconds on generating random numbers. So next, again, you saw this request. You saw a request in the basic setting. Now it's a bit more complex. So we want to see CVA and DVA as output, and we want sensitivities with respect to both of these outputs. So with the rates, the volatilities, and hazard rates. And let's see how it actually performs. If we want to run 5,000 simulations, post-recording, post-random number generation, it takes about 0.6 seconds to do it on a single CPU core. And we can come back to the original program, and we can see that the original program, it took about 27 seconds to run. So it's a healthy acceleration. So we're getting about 30, oh, sorry, more than 30, we're getting about 50x speed up on a single CPU core. But mind you, though, we're not only calculating CVA and DVA here, we're also calculating all sensitivities. So in a time frame of 0.6 seconds, we calculated CVA and DVA and all of its first order sensitivities. We're also able to take advantage of multi-core system, right? So let's see how it performs if we run it on using just 4 CPU cores to get the idea if we're getting the promised benefit of using multiple cores. And indeed we do. So if one core runs in 0.6 seconds, 4 cores can finish it nearly 4 times better. Nice, perfect scaling. And as promised, you get yourself the CVA and DVA, you get the full sensitivity ladder, and expected exposures, right? So what we can do with this next? We have our random numbers in memory, hot, available to us. We have our portfolio recorded and ready to go. So why throw it away? Instead, what we can do, we can create a life risk. So what is life risk? We're just sitting and listening for new market data to come in. And we're rerunning the same recorded kernel with the same random numbers for new market data sample. And how does it look? This is how it looks. You can use this nice Jupyter widgets technique to demonstrate this. So here on the top, I can slide my interest rate curve up and down, and I can immediately see how exposure changes. So here you see the exposure from the simulation, and you see how the sensitivities for CVA DVA change as well. And how long did it take to compute? You can see it's like fraction, 0.17 seconds. Although this time I go a bit further and I do use 100 threads to achieve that. But you're getting to the point where it's almost instant for humans. Right. So so we were able to achieve a performance speed up of about 1,000 by using this clever compiler, but also fairly advanced hardware. So how advanced this hardware is? So what we're doing today, it's powered by latest Intel Xeon Scalable chip, and you can read documentation about this chip here. And what we're looking for here, it's quite impressive hardware, right? So how much it costs? It's not that much. I mean, if you compare this to NVIDIA GPU, it's about the same ballpark. What we're also is looking for here in this hardware, we're looking for technology called AVX 512. The example you saw is currently running on AVX2, and AVX2 has been around for many years. And what's allowing you to do is essentially you get about 4x in double precision with basically a little expense on your part. So your main CPU processor can function as a vector processor, right? It doesn't always have to work in Scala mode. It can work and process not a single Monte Carlo simulation, but it can do 4 Monte Carlo simulations in case of AVX2. And in the case of AVX 512, it can process 8 Monte Carlo simulations. And in fact, Intel engineers, they tried to make this technology as good as possible, and they maybe didn't have much luck in the beginning. In many cases, when you try to enable AVX 512 on your existing quant libraries, you often find you're not gaining much performance. And the reason for this is because compilers, regular compilers, have difficulties identifying vectorization opportunities. So what I'm going to do now, I'm going to demonstrate what Matlogica can do with the AVX 512 technology. So we saw that in AVX2 case, we are running XVA simulations in, let me see, it's somewhere here. So 5,000 simulations we want to do. So it runs in 0.6 seconds on a single CPU core, right? On a 4 CPU core, using four cores, it almost linearly scales. So let's run the same example, but this time we're going to use AVX 512 version of the library. So we are loading a version of the ADC library that supports AVX 512, and we're going to run full Jupyter notebook with that. Skipping through all the boilerplate, getting to the interesting stuff somewhere here. And here we go. So AVX 512 gives you not a double performance, because you're still working with the same memory. You're still limited by your memory bus, but your compute grows almost twofold. So we're getting about 1.8 performance boost by switching to AVX 512 technology. And for 4 cores, we had about 150 milliseconds. We're now in the region of 90 milliseconds, right? And what does it do to life risk? Of course, it helps to life risk, right? So if we're here and we're running 100 CPU cores with the AVX 512, we're getting great speeds. I mean, it does fluctuate a little bit, obviously. So it's Python overall, but you can see the point. Right. So I think we need to move on. If you have any questions, let me know. Yeah. So the next example I want to talk about is how you can see Python and C++ working together. In the previous example, you saw how Python orchestrates calculations on C++ side. So you instantiate some quantitative objects in C++. You put them all together, and ADC is able to record full valuation graph through that. Now, is this all? Like, I mean, can Python and C++ be equal partners in this endeavor? So what I'm going to show now is a basic example where we want to do some calculations on Python side. We want to instantiate some calculations and some objects, sorry, on C++ side. And we want to show how we can record calculations on Python, C++, and how we can propagate sensitivities through this logic. So here we are going to use, again, open source QuantLib for demonstration purposes. And Matlogica ADC, we have experience and we have tooling allowing you to integrate with your proprietary quantitative C++ libraries as well. So if you want to see this done to your inner quantitative library, get in touch with us and we can enable it with the ADC also. Right, so here we have some basic initialization steps you would go if you use some C++ quant library. Here, what's important, you see this curve object constructed from a vector of dates and vector of rates, but a discounting curve is constructed from a vector computed as a spread on top of forecast rates. So this specific operation, this plus, this addition, is handled by Python. But pricing here, the pricing engine, etc., is handled in C++. So in order for us to record the calculations, we must be able to record calculations in Python, and we need to record what's taking place in C++. So we have this pricing function. All you need to know, it takes some dates, a vector of forecast rates, and the spread, and it gives us the price. Internals of this, if you fancy to read about QuantLib, you can do so in your spare time, but it doesn't really matter. All you need to know, it's a bunch of C++ objects created from, in this case, an open source QuantLib library. Now you can run this function as regular. Like here we're outside of recording context, so we can run our pricing function and get the price. We can begin recording our calculations. So just like in a basic example, we need to start recording. We need to identify our inputs. Our inputs in this case, a vector of rates and discount spread. You can see we populated the vector with I double objects. We also mark them as inputs, so the framework knows where your inputs to your evaluation graph and where your leaves are to form the full directed asynclic graph. And next, we run the same pricing function. But this time, the pricing function returns as I double object, and you can see it's being traced, right? You can see these two additional flags telling you this variable is a random variable because it depends on the inputs. And we need to calculate adjoint with respect to this variable. We mark it as output, stop recording as before. We check for consistency with recording, all good. Again, if you want to know and if this check needs to pass, right? So if something is wrong with this check, you're not able to use this recording for arbitrary inputs. If you want to know more about it, come back to us. I don't think we have much time to cover all these subjects. Now we're going to use the same recording, but this time we're going to provide random inputs, and we're going to run it for 10,000 simulations. Here, just a regular Python to create random perturbations for original input vectors and discount spread. Again, the familiar request object telling us we want swap price and we want sensitivity with respect to forecast rates and discount spread. And we're running the evaluate function with 4 multi-thread, and we're getting prices of the portfolio or the trade for each scenario, and we get average sensitivities, average bucketed sensitivities for forecast rates, and we're getting spread risk. And again, so we were able to propagate sensitivities from Python and C++, and this allowed us to get sensitivities with respect to discount spread, which is scalar, and this spread object were never seen by C++. Right? C++, so only a vector of spreads, which is a spread on top of the forecast rate. Now we're going to obviously verify this with bump and revalue. Again, this is something you can play with in your spare time. And we can compare the numbers are the same. Now, yeah, I'm a bit cautious about time, but I think we're going well. So So here you can see we're able to orchestrate calculations from Python, do some calculations on Python side, but also involve some of the C++ components in our relation graph. Now, this is not something you can get from tools such as JAX or PyTorch, etc. Right? So you need to have this active type that can be a first-class citizen on both sides, on C++ and Python, to make it work seamlessly. Now, I'm going to go and jump on a bit more advanced examples built on the previous one. And this is quite interesting. So imagine you're in a situation when you need to come up with a slightly tweaked way to interpolate your discounting curve. For example, someone comes to you and we need now to support rate hike decision dates, right? And for some reason, you didn't have it in your Quant library. So you need to build a new discounting curve that potentially supports tweaked interpolation method where you need to provide some step function. But you don't want, maybe you don't even have access to your QuantLib library, or you don't want to recompile your C++ object. So can you do it from Python? Can you create a new interpolation method on Python side and send this newly created object with its own implementation to C++? So it turns out, yes, you can. That's quite what makes Python so powerful. So just as before, we initialize QuantLib library, we define this spread, but this time we declare a Python class, and we derive it from interface declared on C++. And then inside this interface, we completely change how discount factors are calculated. So this probably not the most exciting interpolation method you've seen, but it gives the point. So you can provide alternative ways how you can interpolate your rates, and by doing so, what you can do next in this function, in the function where you call pricing functions from C++, you can create this customly defined class on Python side, and you can send it to pricing function on C++. And I found it very fascinating. So you now have Python calling pricing function on C++ and C++ calling back to Python for each discount factor. So C++ still holds the logic of how to price the instrument, how to forecast rates, etc., how to generate all the schedule dates. But for every discount factor, it will make a callback to Python, and you can override the behavior. So you may say it's nothing to do with ADC. Yes, it's not really something to do with ADC. We just have a tooling that allow you to do it with your Quant libraries. And we also want to demonstrate recording still works, right? You can still work out all the dependencies from inputs to outputs. And this time I'm going to run all the kernel cells, runs second cells and below. So I'm running all the cells that are similar to what it was before. And we now see additional risk with respect to first two buckets, right? Something we didn't see before. Why we see this risk now? Because our interpolation method uses these two first rates for some reason. But you can define more sophisticated interpolation methods here if you want. So I found this quite interesting. This is something that you may want to work in practice and how you interface with your Quant libraries. And I'm ready to move to the next subject of cloud and serialization. So with the MATLOGIC ADC approach of recording calculations, once you have a recording completed and you pass through a first sample of your program, the recorded kernel, it actually separated from your original analytics, right? It no longer requires your original program to make it run. And what's more, it's actually serializable. So I'm sure many of you are familiar with the pickle interface in Python. So here we have a function recorded from your original analytics involving some Python, some custom objects, some proprietary quantitative library potentially. And all we need to know is the kernel object, the inputs, and the outputs. And we can save it into file. So what we can do next with this? We can go to the other side of equation. And here, what we're going to do, we're going to install ADC library without QuantLib. So it now knows nothing about our quantitative analytics implemented in C++. It has no connection to the original customly defined interpolation method. But it can load the kernel from a file source. Again, the source, you can send this file across the network. You can cache it in some kind of database. You can rerun it as many times as you want throughout your trading day. And the only thing we need to know is the inputs. Here are our inputs and the outputs, right? And just as before, we're setting new inputs to forecast and discount spread. We're simulating new scenarios locally, well, remotely to the original process. We're defining our request, call evaluate, get our prices for the trades under different scenarios, and get the same risk. So you can compare this risk computed before in separate process. Right. So I've been talking a lot, and it's almost near out of the time. I guess, Natalia, did we miss anything? Do we want to cover more?
I think we've covered most of that. Let me just go back to my screen. So we covered the Monte Carlo and the first principles. We looked at the saver volatility, right? XVA life risk, serialization, and using C++ and Python together. And we've just had a brief look at the life risk and the automated implicit function theorem, right?
Yes, correct. Thank you so much. So in the interest of time, I don't know how much time we can use more from this.
I think let's leave some.
Yeah, I invite you to go over this example probably in your spare time. So what happens here, we demonstrate this life risk, but in instance when we have a portfolio that doesn't require Monte Carlo simulations, right? So MATLOGIC ADC was designed to record once and run many times, right? But in some cases, you have a one-off, like what happens in this instance, right? So if you want to see your portfolio of vanilla swaps, swaptions, etc., and you want to see your portfolio updated quickly intraday, this is what life risk is for. You can record your calculations and you can run them intraday for just one-off calculations, but this one-off comes to you with risk as well, right? So I'm can run this runtime quickly and run all to show you how it works. Again, this one works in Google Colab. You can open it and play with it yourself, modify it the way you like. It does use open source QuantLib for pricing functions. Here we simulate the portfolio of random swaps. We record the kernel. So this is now it takes some time to record, but not a huge amount. So in this case, 18 seconds. Google Colab is not the fastest machine, but okay, you spend 18 seconds to record 1,000 interest rate swaps. Now, the original QuantLib takes about 233 milliseconds to just do single valuation. So just a single valuation takes 200 milliseconds. With AADC, you get PV of all your trades and all your first order sensitivities in about 30 milliseconds. But it actually allows you to do more. You can get in the same time frame here in this instance, because it's a scalar calculation, essentially. We don't take advantage of AVX2 or AVX512 vectorizations. So you can, if you want, you can, in the same allotted time, you can fit a ladder risk, right? So you can see how delta risk changes with respect to some pre-configured scenarios, 100 basis point up, down, etc. So here, just another slider that simulates market moves, so you can see how quickly you get updated results.
All right, thank you, Dmitry. I think we're largely done, and we've covered a lot. There's a bunch of things that we haven't covered, and I put them here on the right-hand side. And we haven't talked about the integration approach, about debugging tools, about how you manage branching, if statements, and loops. And this question was raised at least twice in the chat. American Monte Carlo, path-dependent derivatives, scripting payoffs, and different AED approaches. So if you have interest in that, feel free to reach out to dmitry@mathlogica.com, or if you have some time, let's stay on the line for a little bit longer. And we can also do a workshop for you and your team just privately. We will share the recording with everyone via email. You can access the examples that we've just seen using GitHub. We have the private beta of the solution that you can run on your machine available on request. And again, you'll need to email us. We also invite you to join our Discord channel, and you can scan the barcode here to join it. It's new, so don't be afraid that it's a bit empty. And if you have a couple of minutes for feedback, you can scan this green barcode here and answer a couple of questions about how you enjoyed it. So
I see a question from Frankus about consistency checks. So the consistency check makes sure we're not missing any branching within our recording. So this, what it means, if you have if statements that what we consider stochastic, I mean, some Boolean expressions do not depend on your random numbers, nor your market rates. For example, if your trades is expired or not. I think Dmitry replied to that in the channel. But the consistency checks allows you to make sure you didn't miss any of such branching. And if you do, it gives you location of such branch. Like it points directly in the source code where if statement needs to be modified to handle it properly, similar to what we saw before with the stochastic interpolation for local vol. So if you think about it, linear interpolation for local vol, it's full of branches, right? It has this stochastic argument, and you need to pick random points in your curve. So Matlogica can handle this. We can handle this stochastic interpolation easily, and we handle it both ways. We're not only interpolating in this surface, we're also propagating adjoints to proper buckets.
all right, so if you have any questions, please reach out. And otherwise, we will share the recording, the slides, and all the useful links with you in the next couple of days. And thank you, Dmitry, for presenting. Thank you everyone for attending. And thank you, Neil and Jason, for organizing this webinar. Any final thoughts, Dimitri?
Well, there is another question about if kernel function is exact representation of original program. So to answer this, it is exact calculations. We don't do any approximation, any machine learning, any fiddling, changing your analytics. So typically, you see the values within machine precision to your original program. So something typical if you switch a compiler. So if you go from GCC to Clang to Microsoft Visual Studio, you do observe some numerical differences, typically because your operations executed in a different order. So you should see a similar accuracy from our product. All right. Thank you very much. And
yes, thank you.
Have a great weekend, everyone.
Yeah, for anyone coming to Quant Minds or WBS, we'll see you there.